So first of all, thank you for having me and giving me the chance to speak about my work. Today, I'll be talking about what I think is a pretty novel approach to quantum metrology and how we can enhance its performance with quantum cryptography. I'll mostly be talking about the project that we recently worked on that you can find on the archive, but I'll also talk about, above and beyond and a little bit of other works. So I've partitioned this talk into 3 different sections. The first is an overview of quantum metrology. I think a lot of people in this group will be familiar with it, but a refresher is always good. And then I'll talk about some motivation and framework on why you would want to do this. Like I said, some pre-existing references in some old literature and kind of the necessary framework. And then I'll talk about the cryptographic protocols that we constructed in the paper. Right. So first of all, for those unfamiliar, metrology is just the science of measurement, and it's all about accurately measuring some physical quantity and doing this in a reliable and reproducible fashion. And it really is a foundation of science, as science is all about understanding the world around us as precisely as possible. And I think like the recent Fermilab G-2 experiment really resonates with this idea. And it's also a necessity for engineering. I don't think anyone would want to sit on a chair that was constructed where lengths and angles couldn't be measured properly. But as a theorist myself, I think of metrology in a really simple way, where a probe measures some sort of quantity. So for example, in these old tiny thermometers, the mercury inside of it would act as a probe, and it would provide a measure of temperature by expanding or contracting. And in the new laser or infrared thermometers, it would be the emitted light that's acting as a probe, and then expansion of the metal inside the thermometer would be give the measure of a temperature. And quantum metrology is exactly what it sounds like. We're now using a quantum probe to measure some sort of physical quantity, but more so, we want to take advantage of quantum effects to achieve an enhanced measurement precision. And there's a lot of applications for this in material sciences and nanoengineering, where we're looking at measuring magnetometry, thermometry, and all these physical effects. But there's also a high demand in biology and medicine, where maybe damaging or maybe probing a sample is damaging. So if we can use probes, we would, it's obviously advantageous, and the applications are really endless. Like even in 2019, LIGO started upgrading their hardware and their technology to use squeeze light or quantum light instead of Gaussian classical light to achieve a better measurement precision in future gravitational wave experiments. And how this is done, I like to partition quantum metrology into 4 necessary steps. First is some sort of state preparation, where we want to create the quantum state psi, which we will encode with some parameter theta. And without loss of generality, theta can be a vector, it can be multiple parameters. But for the simplicity of this talk, theta is a scalar, but it'll be really easy to extend this to the multi-parameter case. And it's encoded, most of the time we think of some sort of unitary encoding, but without loss of generality, again, it can be any sort of completely positive trace preserving map. And then what we do with these states is measure it in some fashion. And if we do this enough times, then we can construct an estimate by reverse engineering the measurement statistics. And since we don't have an infinite number of resources, there's going to be some sort of error associated with our estimate. And so I'll go over this common statistical nomenclature for quantum metrology that won't be so important for the crypto part of the talk, but I think it's important to have in the back of our minds regardless. So Fisher information is just this quantity which measures the amount of extractable information a probability distribution has about an unknown parameter or a random variable, or a probability distribution has. And so in this quantum case, we're thinking about the extractable information a specific statistical distribution has. And the quantum Fisher information, we're now just maximizing this. So we'll maximize over all possible measurement schemes. And the Kramer-Rao bound is this inequality which relates the variance to the unknown parameter and the inverse of the Fisher information. And in the multi-parameter case, this extends to some sort of matrix inequality. And then even if you're unfamiliar with quantum metrology, you've probably heard of Heisenberg limited sensing or the Heisenberg limit. And I'm pretty sure this comes from the fact that if you compute the quantum Fisher information for doing phase estimation with a pure state, where the unitary is generated by some Hamiltonian H, or the phase encoding unitary, and you look at the quantum Kramer-Rao bound again, then you get something that looks like the Heisenberg uncertainty principle, hence the name Heisenberg limit. And the Heisenberg limit is achieved when this bound is saturated. But what we are more concerned with is how the variance scales with a specific measurement strategy. And what we'll be looking at specifically is when we measure some sort of observable and use the measurement statistics to actually first construct an estimate of the expectation value, which should depend, if you picked a good observable to measure, this should depend on the unknown parameter theta. And so we can then invert our estimate to obtain of the expectation value to obtain an estimate of theta hat, or the unknown parameter. And if you remember from undergraduate labs in physics, when you invert a function, the error, you can compute the error with the error propagation formula, which just reads something like the variance over the derivative squared. And this mu is the number of resources used. So it's the number of states you encoded and the number of measurements you made. And a quick and easy example, just comparing the classical regime to a quantum regime, we have the phase encoding or phase estimation, and we'll come back to this example a few times during the talk. And in the classical analog, we have no sort of entanglement. And in the quantum realm, we have a maximally entangled GHZ state. And if you do the computation where the observable you pick is some observable orthogonal to Z, so it can be X, Y, or any linear combination, you'll find in the quantum case, we've picked up this quadratic term in the denominator. And this is the so-called Heisenberg limit, where we've greatly increased the precision by using the same number of resources. And so why would you want to include cryptography? As it doesn't seem obvious right now. And to motivate you, I've brought back this graphic where I have prepare, encode, measure, and estimate. And generally, most people would assume that everything is done at one location, or one physical location, or it's done by one party. But that doesn't necessarily have to be true. We can think of some sort of metrology scheme where there's spatial separation is natural, such as clock synchronization, or maybe large-scale gradient sensing or large-scale imaging. We could also think of a scheme in the near future, maybe where some quantum technologies are more accessible than others, and you can prepare and encode states, but you don't have the ability to measure a quantum state, so you have to delegate this task to an outside party. Or maybe you just want some sense of security or privacy. And to achieve this, to perform quantum metrology in this setting, we have to ensure some sort of security. And the only way to really go about this is to now incorporate a quantum cryptography protocol with our quantum metrology scheme. And so I'm going to, before laying out the framework that I've listed in the paper and the protocol, I'm going to go through some previous mentions in the literature, as it's not the first time that it comes up, but it is relatively new. And the first time I saw a security mention in a quantum metrology paper was this a quantum networks of clocks in 2014, and it very much is a clock synchronization setup. And for those who aren't aware, clock synchronization, we have all these qubits that tick at the same rate, and sometimes they get dephased, and we just want to make sure that we put them back in sync by sending the appropriate correction. And so we're measuring the dephasing. We're trying to estimate the dephasing. And security here wasn't the main focus. It really is just a small section. But what they say is that they can detect any sort of malicious activity at one of these external nodes if they occasionally send these decoy qubits with a known statistical distribution. And then they also say that it's private just because they have classical encrypted communication. And I don't want to dwell on these past examples too much. They're just for a brief kind of extra bit of knowledge. And the second example that I want to bring up, and I think this one actually handled it the best, was this paper from the NTT group in Japan, where they look at quantum remote sensing with asymmetric information gain. And this is an example where the task is delegated. So you have access to, you can prepare and you can encode the quantum state, but you don't have access to a measurement device. And what they do is they then send the measurement info to some sort of server, some sort of untrusted server, and they encrypt it using blind quantum computing algorithms. I'm not going to spend time introducing what blind quantum computing is. It's a little bit complicated, but it's kind of this encrypted hybrid quantum classical security scheme. And then finally, what our work was kind of motivated from the most, I think, is this very recent paper called Cryptographic Quantum Metrology. And here, there's two parties. One party can do the encoding, and one party who is both on the left end and the right end can prepare and measure the sample. And to actually exchange the quantum states, they have to send it through some sort of quantum channel that's untrusted. There might be some sort of malicious adversary listening in, and they want to do this phase estimation. But the problem is, if there is a malicious adversary and there's no cryptography protocol, then Eve could just bias it, or they could learn phi for themselves in this case. And the protocol that they come up with is that by sometimes doing deterministic actions. So instead of always sending a GHZ-like state, sometimes Alice will just, or sometimes this party will just send 0 or 1, some computational basis state, which with a known measurement. And sometimes the party in charge of encoding won't encode the parameter, but a known phase. Then these additional deterministic actions will dissuade Eve from learning anything about the phase, and it will provide a sense of security because if there is no malicious actions, all of these results are deterministic. And all three of these are okay, but I think there's a lot to build from. And one thing that was really missing from all of these, I didn't include it, but you'll just have to take my word is that this question I don't think was properly answered. So is this equation still true in a cryptographic setting? And the answer is obviously no. As soon as you introduce a malicious adversary, you're adding additional uncertainty in your setup, either your measurement or the final encoding state, but there is additional uncertainty. So we have to modify this somehow. And how we go about this in our work is we really want to tie together these cryptographic quantifiers to these metrological quantifiers. So in cryptography, we have notions of privacy and notions of soundness, which I'll explain shortly. And in metrology, we are constructing an estimate and we want to achieve some sort of precision. And in our paper, when the terminology we use, we say that some sort of protocol has integrity something, or some sort of cryptographically enhanced quantum metrology protocol has integrity blah. So how do we go about actually linking these two things together? We should first compare a general framework for an ideal scenario versus something that might be malicious. And in this ideal framework, we have new quantum states, so the total number of resources, and rho theta, some sort of encoded state that we'll measure. And in the malicious, and maybe this is actually a poor choice of word, maybe it should be potentially malicious. It's just that we don't know. The overall quantum state is rho prime. It's no longer necessarily IID or independently and identically distributed. There could be additional entanglement. It might not have to do with theta at all. Like it could have been replaced by something else. The point is we don't know. There's now uncertainty in our resource. But to actually do quantum metrology, the state has to be at least close to what we're thinking of. Otherwise, what's the point? So we demand that our quantum state obeys this inequality, where d is the trace distance, and this bracket j is, or this superscript bracket j just denotes the jth block of n qubits. So you can kind of think of this as saying the average distance to the ideal state is pretty small, or maybe that the total uncertainty, you can maybe think of this as like the uncertainty in your resource. And what we actually want in our work is for this to actually be useful and practical, we just say that epsilon squared is much less than 1.
Sorry, Nathan, may I ask a question?
Yes, of course.
So by looking at reduced density matrix, do you not constrain to somehow local measurements? Is this not an issue that?
Yes, so we're constraining ourselves to local measurements in the end.
Okay, so so basically you give mu copies, but the adversary, neither the second party, they won't be doing global measurements on all the copies in your scheme.
No, at the end it's only local measurements.
Okay, thanks.
Yeah, good question. And I guess if there are any questions in the middle of the talk, feel free to ask. But so in doing so, as long as this epsilon is small, it shouldn't be too hard to imagine that a good strategy is to do what we were doing and just pretend that we had the good state. So what I mean is we're still going to measure the same observable O, and then we're going to pretend that we measured a bunch of copies of rho theta so that the expectation value is some function, it's the trace of O rho theta, and then we'll invert that equation. Because of this isn't perfect, there's now, additional uncertainty in the quantum state. So our estimate, which I've, in the malicious case, I've labeled with a prime, is now additionally biased by some amount, where this little o is the maximum magnitude of the eigenvalues of O. And this then translates to an added or an increase in variance by this quantity here. And for those that might be concerned with the 1 over the derivative, this shouldn't be too surprising because it also appeared in the error propagation formula, but all it's really saying is like if your derivative is at some sort of global maxima and there's any sort of error, then it will be much more influential than if it was, rising really quickly, where now when you invert it, it won't matter so much. And at that global maxima, this will be closer to 0, so it'll be a larger difference. So what does this mean? This is the second time we revisit the GHZ example for phase estimation. I'll visit again once more at the end, but you'll just have to take my word that we can always kind of construct an observable that where the derivative is more or less n. And looking at the equations, we see that the variance is now bounded by one term that's like epsilon over nu, and one term which is like epsilon squared over n squared, or I guess this one's epsilon over nu n squared. And so if we want something that kind of looks like the Heisenberg limit, obviously it's not the exact Heisenberg limit, but on the order, we would need our uncertainty in our estimate to scale like 1 over nu, or 1 over the square root of nu. And this makes a lot of sense because in the perfect world where the number of resources tends, as the number of resources tend to infinity, we're obtaining, or our variance goes to 0. And so if we want to keep this in some sort of malicious setting, we need to make sure that the added variance with the uncertainty in our resource also goes to 0. And so now I'll actually try and link this to soundness. And so I want to introduce two notions from cryptography. The first one is privacy, and it's a lot more straightforward of the two. It's just stating that there's no extractable information. And by that, I mean that any sort of malicious adversary can't determine the unknown parameter for themselves. I'll give a mathematical formula for that later on. And soundness is a little bit more difficult to explain. If you're familiar with crypto, this might not be the formula that you're most familiar with, but I think it's the one that's it's the easiest to explain to someone unfamiliar, and it really actually only holds when the ideal state is pure. So soundness, I've written that it's the ability to detect alterations made by a malicious adversary. And in the equation, we have three, so F is fidelity, and this is a probability. Rho ID is going to be the ideal state. So it's rho theta in this case, and rho out is going to be your output state. So most cryptographic protocols have two outputs. One is a binary accept reject. And by this, I mean that if we accept, that means that we've accepted that no alterations were made. It's not the same thing as no alterations were made. It's that we've accepted that no alterations were made. I hope that's clear. If not, I think it will be more clear when I actually go through the protocol. And then the output state is going to be the output state we use for whatever our heart's desire. In this case, it's going to be for quantum metrology. And so this is really saying that the probability of accepting that there were no alterations were made, and 1 minus the fidelity of the ideal state rho theta and the actual output state is small, or less than or equal to delta. Does that make sense to everyone? Okay. I think it'll be a bit more clear once I actually outline a protocol, so you can get a notion of p-accept. So we still actually can't link this to epsilon yet. So we have to make one more assumption, and that's that p-accept is greater or equal to some alpha, or it's lower bounded. And in theory, this doesn't have to necessarily be true, but in practice, it's generally alpha is probably close to 1. It's either going to be some sort of maybe accessibility to the quantum channel, or maybe your malicious adversary isn't all powerful. They can only do limited kind of things. But we have to make this assumption to move forward. And so I can just give you an example why. We can, if, for example, a malicious adversary, or I'll give you an example why it's not necessarily in theory true, but if a malicious adversary replaced everything with the maximally mixed state, then I'll claim that whatever test you're doing to try and detect will always have some small probability of passing or you accepting it. And then the remaining state, or the output state, is still maximally mixed, and so obviously totally useless for quantum metrology. But we have to make this distinct, or we have to make this inequality hold to move forward. And in practice, it's fine, and it's done quite frequently. Sometimes in crypto, it's referred to as like statistical significance, but I digress. But in doing so, we can now kind of pull this out of the equation, and I've rewritten it where I've absorbed the expectation value into the output state. So now rho out is really, here is the expected output. And there are numerous inequalities relating fidelity and trace distance. I don't remember what they're called, but we can now set epsilon from previous slides to the square root of delta over alpha. And so now we have this connection to soundness and the variance, or the bias in the metrology scheme. So what we're going to look at is the same one, or the same kind of example from the third paper that I mentioned, where we want to do quantum metrology. We are Alice and Bob, and there could be some sort of malicious adversary Eve, where Alice wants to prepare, or Alice has the ability to prepare states and measure quantum states, but we have to send it to Bob to actually encode the quantum state. And to send it, or to send and receive, we use some sort of quantum channel, which may be untrusted. We don't know if there's a malicious adversary or not, but we want to prepare ourselves just in case. And to do so, we design two protocols. I write protocols with an S because it's really one protocol disguised as two, where we have some sort of input state, which will be somewhat for quantum metrology and somewhat for the cryptographic protocol. And then we'll have some sort of output state. Bob only has the encode or the parameter encoding, which is some general CPTB map. And then we're going to perform some sort of encryption and decryption algorithm. So these scripted E's and D's just signify encryption and decryption, where the subscript K1 and K2 are classical keys, which Alice and Bob shares through some sort of secure quantum channel. And we assume nothing about Eve. They can do anything they want. They can store or inject quantum states, really any sort of CPTB map gamma. So in crypto, I think that's referred to as computationally secure when you don't assume anything about your adversary. And this is where I hope that the accept and reject will make a little bit more sense. So our input state is going to be some sort of quantum state for metrology, and then some sort of decoy quantum state where we have T decoy qubits, all just in the computational basis 0. And if there was no malicious adversary, at the end of this, we expect, we fully expect these decoy qubits to still be registered as 0 tensor T. And so if Alice measures them in 0 tensor T, then we accept that no alterations by a malicious adversary were made. And if not, then obviously there was somebody tampered with the quantum state and we're just going to discard it. And that doesn't mean, like, just because we did measure 0 doesn't mean that Eve didn't tamper with the quantum state. So I think that should have made more sense than before. And the
Nathan, so surely, I mean, you should permute these qubits, yes, or whatever.
You do. Yeah, it's not necessarily metrology tensor. This I just didn't put.
And of course, this 0 just is chosen as some eigenvector of the generator of this encoding, yes.
Yes. Yeah.
Not to change under parameter encoding.
Yep. Okay. Precisely.
Yeah.
It was just that was a little much to fully write in, but you're right. It's always permuted. And it's just something that's not affected. And then, so I write that it's, again, as protocols and not protocol, because they're effectively the same thing with different hardware assumptions. So the trap code, which is the easier one to implement, is when our encryption and decryption is done by first order Clifford operations. And first order Clifford operations, for those who don't know, are the Pauli group are closed under all Clifford operations. And they're also easy to simulate classically. And the Clifford code is the nth order, or where encryption and decryption algorithms are taken from the nth order Clifford group. So much more complicated to implement, but obviously it's going to be more secure, where M is the total number of qubits, n plus T. So in doing so, we first achieve total privacy. So anytime Eve accesses the quantum channel, the state that she sees is the maximally mixed state. And this is just a corollary of the Pauli twirling lemma for those who are familiar with it, relatively easy to prove. And we also get some notion of soundness. So for the simpler protocol, the trap code, we get this 1/T like scaling in the denominator for the soundness. And the Clifford code, we have this exponential 1/2 to the T scaling. And like I said, this isn't too surprising, because if
Nathan, sorry. Yep. So you assume that they share some key.
Yeah, yeah. Like I said, so they picked from
Okay.
random or is randomly chosen beforehand, and they share it through some sort of classical communication channel that is, we assume, to be secure. If Eve has access to one or two of these keys, we could no longer say these things.
Okay, sure. Okay.
But as I was saying, this 1 over 2 to the t, this huge increase isn't too shocking because a general operation from the nth order Clifford group will be will generally generate entanglement. So now if Eve touches any of the quantum states, even one for metrology, it will probably propagate to one of these decoy qubits. And so the probability of Alice rejecting is lower or higher. And so finally, I want to translate this one more time to the GHZ example. And if we recall, we needed this kind of uncertainty in our resource to be 1 over the square root of the total number of resources. So if we look at our protocol, we are now recovering the Heisenberg limit where each round, the decoy qubits scales like 3n nu over alpha. And I do want to say again that in general, alpha will be close to 1. It's sometimes chosen either 0.9, 0.95, or 0.99. Those are pretty common values. Or Clifford, it's going to be this logarithmic term. And this isn't, this is each round. So we do have to note that you have to do this nu times, or the total number of resources you want to use. So in general, we would need some sort of quadratic increase in the total number of resources, or this log linear increase, which isn't too bad, all things considered. So to summarize what we've done thus far, and then I'll get into kind of some outlooks. In our work, I think we were really the first ones to properly address a cryptographic framework for quantum metrology. And we did that by linking these crypto quantities and these metrology quantities, namely the soundness and the variance. And then just as an example, we constructed a secure and private protocol for quantum metrology over an unsecured quantum channel. And I didn't mention this, but the other protocol that did it, in 2019, we actually showed that their protocol wasn't secure or private. So that means that Eve could, or we proved in our paper that using their protocol, Eve could gain an estimate of theta and go completely undetected. So it would completely fool them. And then our protocol now, depending on the hardware assumptions, to maintain some sort of Heisenberg limited sensing for phase estimation, we would either need a quadratic increase in the total number of resources or a log linear increase in total number of resources. But like I said, this is a relatively new area of study, and there's a lot of things that I think can still be done. And actually, I'm working on like a part 2 of the project right now. We didn't finish it, so I couldn't include it in here. But I think there's still a lot of general questions to open. So the biggest one, or the easiest one I think to tackle, is multi-parameter. I think everything, even though I didn't touch it in the paper, I think it would be easy to expand to that universe. And then I would also like to generalize this to the continuous variable setting, which in general is a little bit more complicated. And then there's also, this protocol was a very general scenario, but sometimes we want specificity. So either, some sort of implementation, like a photonic quantum channel might be open to different attacks to some sort of distant NV center implementation. And then some attacks are more common but easier to secure against than others. So it would just be looking at specificity and kind of what maybe can be realized in a lab. I think that would be interesting. And then what I didn't touch on here was the whole delegated quantum metrology. What happens if, you know, we have to ask some sort of third party to do the parameter encoding. There's a lot that we can go upon here. With that in mind, I want to thank you guys for, again, having me and inviting me for this seminar. I hope you learned a lot today, and any questions, I guess.
Yes, thank you very much, Nathan. So let me open the floor for questions. I see I'm looking at the chat, but also Rafa is unmuted, so I'll pass him the mic.
Yeah, okay, so maybe I can just ask one question first. So I was, okay, when I saw your title of your talk, I was expecting that you will combine in a single protocol, like quantum metrology sensing and quantum cryptographic protocol, which does not require, you know, this pre-established shared keys, something like this. So I was wondering if you thought about this direction to have a protocol which does everything quantum, like simultaneously somehow. I don't know. Something like this.
We originally actually tried this, and we quickly realized that it was impossible, at least for the setup that we have, where the state has to go through twice, because a malicious adversary could always do some sort of simple Pauli attack and be totally undetectable. That isn't to say that it's not impossible. It's just this specific framework, it can't be done with no assumptions on Eve. You could modify it to do this. It's just it doesn't work for this.
Okay, I was wondering, could one not, for example, ask a simple question and restrict Eve to be doing like some kind of individual attack? So some kind of, she can only measure and send classical information or encode a diagonal state forward.
Yeah, that's one of the things that I want to explore in the future, is making this more efficient when we reduce Eve's capability. So we didn't do it in here, but I would be much more interested, as I think it's a kind of more realistic attack version, and will likely do a lot better the soundness.
Okay, maybe
but we haven't looked at it yet.
I'm wondering, because there's also this, you could treat this problem as an information communication problem, and there's this rate distortion theory that tells you about relates some kind of variance to the shared so mutual information between two parties. So that was when I was listening to your talk, I was just wondering whether, because you really related soundness to kind of Bour's distance, to be honest, right? Soundness to Bour's distance and Bour's distance to variance. And I was wondering whoever this rate, I mean, if I looked at your problem in the classical way, I have three parties that have three random variables. And then could I not tackle it like from information theoretical approaches? This was my...
I think you definitely could. That's a really interesting perspective that I'll have to explore in the future, because I think it would work. We just have to, we would have to change our, like, the foundation, but I don't think it would be extremely complicated to take this route instead.
Mm-hmm. Okay.
As it would be like it would be a very natural jump to go from this shared information to these kind of new formula.
Okay. Okay. Any more questions from the floor?
Like that equation kind of, you can kind of think about it as like leaked information or like lost.
Mm-hmm.
So I think it would work. I would have to look at it a bit more, but I think it would be another very natural approach.
Okay, because I
maybe I can have one more comment.
Sure.
Because you mentioned that this multi-parameter metrology would not introduce significantly anything new. But if you have a model where you basically have like all the parameters, for example, that can non-trivially change every state, then you don't have the zero state that are unchanged.
Yes,
So
you would have
what would you
to
do
change
then?
your protocol. You have to introduce one more quantum key one more classical key, which Alice and Bob share, which is the location of your metrology qubits. So it does get a little more technical, but with an additional quantum key, you could do this.
Oh, but then, okay, playing devil's advocate, could one not argue that in this classical channel, you could just encode the parameter in some binary? Is this not some kind of, because
I suppose you could, but then you're losing. But maybe you can't you cannot just encode. Maybe it's strictly a parameter which it's easier to encode on some sort of quantum.
you just get, I understand, you just get
Yeah.
a box that takes quantum states in and gets quantum states out. You don't really know what it does, kind of.
Yes.
So you don't have a number that you can translate onto some piece of paper.
Yeah, precisely. But yeah, you could, and then you're just arguing about, well, what is more resource efficient, and so it would depend on how
so
many
then you
resources
should then
need.
say that in your protocol, Bob doesn't actually knows the value of theta, no?
Yeah, Bob does not know the value of theta.
Yes, okay, then it makes sense. So are there any more questions from anyone? Please unmute. Don't be shy.
Yeah, so maybe I have one.
Sure.
So is your result in any way related to this covered sensing, where you also have an adversary, but and you want to make your sensing protocol in such a way that the adversary does not know that, well, you are performing the protocol?
Well, they don't know that. Well, the adversary, they might know that we are performing the protocol, so it's not exactly the same thing, but they can't determine the results of the protocol for themselves. So it is kind of like it, but it's not the same thing. Yeah, it's not exactly the same thing.
Okay. Anything more from the floor? We've already asked of Rafael, maybe someone else. Well, then I think we should close the official session. Thank you, Nathan, once more for explaining everything.
Thank you for having me.